Today I'm going to show you a state space representation example that is a little bit more complicated than the simple example we did in the last video. For this example, we're looking at the little electric car where our voltage applied is the input and the horizontal velocity of the car is the output. We're assuming that our electric motor has resistance and inductance. And we're assuming that our motor is a DC motor so that it follows our two motor laws, which is that the torque of the motor is equal to K times the current, and that the voltage across the motor is equal to K times the rotational velocity. If you remember from the modeling example that we did when we found the transfer function for this system, you would remember that we went through a couple of modeling steps to get the differential equations. The first step we applied was we applied the Kirchhoff's voltage law to the circuit, and we said that the applied voltage was equal to the voltage lost in the resistor plus the voltage lost in the inductor plus the voltage lost in the motor, which would be K omega. The next thing we did is we summed the torques in the wheel, and so we said that J, that is the rotational inertia of the motor and the wheels together, times the rotational acceleration is equal to the torque of the motor, which is trying to get the wheels to turn forwards, minus some damping, which gives us a torque in the opposite direction, so it's negative, plus the force of friction times the radius of the wheels. So this is the torque that's applied to the wheel that comes from the contact between the wheel and the floor. Lastly, we summed the forces on the mass. So we said that the mass of the car times the acceleration of the car is equal to the negative force of friction, which is trying to slow the car down, minus some damping, which is also slowing the car down. Now, even though we've shown the force of friction as being negative here, the force of friction will actually end up moving the car forwards because the force of friction causes these wheels to turn, as we've shown up here in this second equation. Now, there are a couple of additional equations that we can use. In addition to these three equations that we have here, and the two motor equations, which we've written up top, one other equation that we have is the equation that tells us that the wheels are not slipping. Since the wheels do not slip, we know that the velocity of the car is equal to the radius of the wheels times however fast the wheels are spinning. Now, with these two motor laws, I'm going to take this one that relates torque to current and I'm going to move it down to the list of our other equations, because we've already used this motor equation in these equations that we have here to substitute in for the voltage of the motor, but we haven't really used this torque equation yet. So I'm going to put it in my list as an equation that we haven't used yet. Now, we have everything we need here to find the transfer function between the applied voltage and the velocity of the car. When we did that, the way we found the transfer function was by taking the Laplace transform of each of these equations and then algebraically substituting one into another until the only signal we had left was the input signal and the output signal, and all of the other signals had been eliminated. Today we're going to find a model for the motor and the car that is not a transfer function, we're going to find the state space representation of this model. So we don't need to take the Laplace transform at all. Instead of using the Laplace transform to convert these equations into algebraic equations, instead we're going to use the state space representation to convert them into matrices, or a linear algebra representation. The first thing we need to do to find our state space representation is figure out how many states we need. The way we do that is by looking at our equations and finding any of the signals that have more than one derivative or integral. And we need to figure out how many derivatives or integrals each signal has, if it has more than one. So I'll give you an example here. We have here the signal omega, and we also have omega dot. So the signal omega has two orders of its derivative. We have the 0th order and the 1st order, so those are two orders. I'm going to now go down into my list of number of states, and since I found a signal with two orders, I'm going to subtract 1 from that, and I'm going to write that down. 1 for the signal omega. Some of the signals that I have here do not have more than one order of derivative. For example, here I have the signal torque, and I have torque down here also. I don't have anywhere the first derivative of torque or the integral of torque. There are no other orders of torque. So torque will not be required to give me any number of states. Torque will give me 0 states, so I can ignore torque for the moment. Another signal that will contribute to my number of states is current, because here I have the derivative of current, and here I have the 0th derivative of current. So current is going to give me 1 state also, because I take the number of orders of derivatives and I subtract 1. So I'm going to get 1 state for current. Now, are there any other signals here that have more than 1 orders of the derivatives? I see I have one more signal here, and that is the velocity. The velocity of the car has the 0th order and the 1st order derivative, so that will also give me 1 state. Now, it's true that V is actually my output signal, and that's okay. Your output signal does not have to be a state, but it can be a state. And since I have two orders of derivatives of velocity, I'm going to need 1 state for that signal. So there are other signals that I haven't accounted for. For example, I have the force of friction here and here. But I can see that force of friction will not require me to have any additional states, because I do not have any derivatives or integrals of force of friction. Since I've identified all of the signals that have more than 1 orders of its derivative, I've figured out how many states I need. So I'll take these and I'll add them together, and I see that I need 3 states. I've also already identified what my 3 states will need to be. Remember that the way you pick out which signals will be your states is that you take every derivative order up to but not including the highest order, and that has to be in your state vector. So in our equations we have omega and we also have omega dot. That means that we need to have a state for omega, but we do not need a state for omega dot. Same thing with current and velocity. We have current and current dot. I don't need the highest order derivative, so I just need one state for current. And for the velocity, I have velocity and velocity dot. That means that I need one state for velocity, but not for velocity dot. So my state vector here is going to be equal to omega I and V. It actually doesn't matter what order you put these in. I could have put current first and velocity second and rotational velocity third. You can put them in whatever order you want. So since this is my state vector, I also know what the derivative of my state vector is going to be. It's going to be omega dot first, and then current dot second, and velocity dot third. I can also identify right away what is my U, or input signal, and that is the applied voltage. And my output signal in this case is actually one of my states. It's going to be V of t. So now that I've identified what each of my state space representations is going to be, let's write out the state space form that we're trying to match. So the first equation in state space looks like this. The derivative of the state vector is equal to the matrix A, and this should not have a dot there. The matrix A times the state vector plus the matrix B times the input. And remember that the input could be a vector if you had more than one input. I'm just writing it as a scalar since in this class we're focusing on SISO, that is single input, single output systems. So let's take this equation and let's translate it with the actual variables that we have identified. So we have omega dot, current dot. I'm going to drop the t's just to save a little bit of space here, is equal to some matrix times my state vector, which will be omega I V, plus this is going to be a column vector times U, which is VA of t. So our task is to fill in these matrices A and B. We also have a second equation in our state space form, which looks like this. Y is equal to C times the state vector plus D times the input. So let's translate that into our variables. Our Y, which is the output, is V, and then we have a row vector that's being multiplied by our state vector of omega IV plus some value here times U, which is our input, VA of t. So now let's look back at our equations and let's see what we can fill in. When we look at our equations and try to get these matrices from our equations, we're trying to find an equation which we can solve for one of our state variable derivatives. And what we will have left on the right hand side of that equation is just our state variables and the input. If I take a look at equation 1 here, this equation is pretty useful to me. I could solve this equation for I dot, and what I would have on the other side of the equation would be omega, which is one of my state variables, I, which is one of my state variables, and VA, which is my input. So that would actually give me one of the rows of my matrices. So I'm going to go ahead and solve equation 1 for I dot. There we go, and I'm going to take this equation and fill it in my matrix. So this is going to go into row 2 because this is the equation that is solved for I dot. And I'm going to start out and pull out the coefficient that goes in front of omega. That coefficient is negative k over L. So I'm going to put negative k over L right there. And the next thing I need is the coefficient that goes in front of I. And the coefficient in front of I is here, negative r over L. And then I need the coefficient that goes in front of velocity. I have no velocity in my equation, so that coefficient is going to be 0. And lastly, I need the coefficient that goes in front of my input, VA. That coefficient comes from right here. It's going to be 1 over L. Okay, so I'm completely done with this whole row. I want to go and look at my equations again and see if I can get an equation to be solved for omega dot or V dot. Let's take a look at our equations. I actually have two equations here that could be solved for omega dot or V dot. I've got an omega dot equation here and a V dot equation here. Now I can see that I can't use either one of these equations directly because these equations both have some signals that are not state variables or my input. In this equation 2 right here, we'll call this equation 2, I have torque, and that is not one of my state variables or my input. I also have force of friction, which is not a state variable or my input. So I'm going to see if I can use some of my other equations to substitute in for these things so that I end up with only things that are my state variables. So to get rid of torque, that one's pretty easy. I could take this equation down here and that would substitute in for torque and give me current instead. Since current is one of my state variables, that's going to help me a lot. So I'm going to go ahead and do that. I'll number the rest of these equations here so I can keep track of what I'm doing. I'm going to take equation 5 and I'm going to plug it into equation 2. Okay, so now I still need to get rid of force of friction. I see that the other place I have force of friction is in equation 3. So now what I'm going to do is I'm going to take equation 3, solve it for force of friction, and plug it in to here. We'll call this equation 6. So I'm going to take equation 3 and plug it in to equation 6. So I've gotten rid of the force of friction here. However, I still can't use this equation 7 directly in my state space representation. Can you see what's wrong here that won't let me use this? V dot is a derivative of my state of a state variable, but it is not a state variable itself. So if I try and use this equation to fill in for omega dot, there's going to be no place for me to put the coefficient in front of V dot, even though I do need an equation for V dot as well. So the way that I'm going to fix this is by using equation 4. If I would take equation 4 and take the derivative of both sides of that equation, I could then substitute in for V dot and pull that omega dot over to the other side, and that would allow me to get one equation for omega dot in terms of everything else. So let's do that now. I'm going to start by taking the derivative of equation 4. Now, I'll call that equation 8. I'm going to plug equation 8 into equation 7. Now I'm going to take this omega dot term and pull it over to the other side to lump these omega dot terms together. Lastly, I'm going to go ahead and solve this equation for omega dot. Okay, now I have an equation for omega dot that only has my state variables. So I can now take this equation and use it in one of the rows of my state representation. So the coefficient in front of I is k over j plus r squared m. So I've taken the row that is for omega dot, and I've filled in the coefficient that will go in front of I as k over j plus r squared m. Let's now go pull out the coefficient in front of omega. The coefficient in front of omega is going to be negative b1 over j plus r squared m. And now I need the coefficient in front of v, which is negative rb2 over j plus r squared m. This equation has no coefficient in front of VA, so I'm going to put a 0 there. Now, I still need an equation for V dot in terms of my state variables. So let's go back and look at our equations and see what I can do here. In order to find my equation for omega dot, I used equation 8 to substitute in for v dot. If I wanted instead to get an equation for v dot, I could have taken this equation and plugged it in for omega dot instead. So that's what I'm going to do. I'm going to go back up here and give myself some space, and instead of using this to plug in for v dot, I'm going to plug it in for omega dot. Now I'm going to group together my v dot terms. And I'm going to finally solve this equation for v dot. Now you'll notice that I'm writing this coefficient a little bit differently. What I did is I multiplied the numerator and the denominator both by r after I had pulled this term here over to the right side. So when I divided through by this term, I would have gotten k over j over r plus rm. So then I multiplied the numerator and the denominator by r to get me kr, and then it canceled out the r here and gave me an r squared in this term. That's where this j plus r squared m came from. I'm going to take each of these coefficients now and write them into my matrix. So the coefficient in front of I is kr over j plus r squared m. The coefficient in front of omega is negative b1r over j plus r squared m. And the coefficient in front of v is negative b2r squared over j plus r squared m. And once again, there's no VA here. So now the last thing I have to do is get the coefficients for my output. I need an equation that is solved for v. Now that's actually pretty easy to do from the equations that I have. I have this equation 4 that says that v is equal to r omega. So all I need to do in this equation is get me an r there, and 0 in front of the others, and 0 in front of VA. Now the last thing I'm going to do is I'm going to write out my matrices a little bit bigger, since they're all kind of squished here, so you can see what each of these matrices are. And in fact, these matrices, you'll remember, is what defines the system. So once I have my A, B, C, and D matrices, we can simulate the system in MATLAB. So what I'm going to do to try and simplify this, I'm going to have alpha represent j plus r squared m, and that will make it easier for me to write out the matrices. So here's our A matrix that you should end up with, and then we have the B matrix, which is 0, 1 over L, 0, and then we have the C matrix, which is just R, 0, 0. And we have D, which in our case is just a scalar, and it is 0. And this is all you need to go ahead and simulate the system.